In this video, we're going to calculate the concentration of all the reactants and products at equilibrium. We're given the equilibrium constant for this reaction, which is 0.811 at 25 degrees Celsius. We're also given the initial conditions for the concentration of hydrogen gas, chlorine gas, and HCl. Our next step is to define the change variable for this particular reaction. Notice that if 1 mole of hydrogen gas is consumed, you would generate 2 moles of HCl. Also, if 1 mole of hydrogen gas is consumed, you would at the same time be consuming 1 mole of chlorine gas. Based on the starting concentrations given, we're unable to predict, just by inspection, whether the reaction will progress in the forward direction to form more products, or if the reaction will progress in the reverse direction to form more reactants. The important thing when assigning the change variable is that the sign of the change variable is the same for all the reactants, and that it is opposite for all the products. What I mean is that the change variable needs to be negative for all the reactants and needs to be positive for the products, or it needs to be positive for all the reactants and negative for the products. So let's set it up just to, for this example, to have the change variable negative for the reactants and positive for the product. So we're guessing that the reaction will progress in the forward direction. It doesn't really matter, and in the end of the video I'll show you what the calculation would look like if we switched the sign. It turns out we'll get the same answer. So let's define the change variables. For hydrogen gas, we would lose 1x, so we'll define the change variable to be minus 1x. For chlorine, it would be minus 1x as well. And then for HCl gas, it would be plus 2x. Notice I'm simply using the stoichiometric coefficients for the reactants and products in front of the change variable. Now let's fill out the equilibrium row. Here we're going to use the initial concentration, and then we will add to that initial concentration the change. So for hydrogen gas, it'll be 2.8 molar plus a negative x. For chlorine gas, it'll be 1.5 molar plus a negative x. And for HCl, it'll be 0.6 molar plus 2x. The next step is to write the reaction quotient, or the law of mass action. So we need to write the concentration of the products over the reactants raised to their stoichiometric coefficients, and then we will plug in the expressions we've written for the concentration of those reactants and products at equilibrium. So first let's write the law of mass action, the concentration of products over reactants for this reaction. Next, we'll use the expressions we've written for the concentration of the products and the reactants at equilibrium in our table above, and we'll fill in the law of mass action below with those expressions. We know that at equilibrium, this law of mass action, the expression I just wrote, must be equal to 0.811, or the equilibrium constant. The next task for us is to use the quadratic formula to find which value of x makes this mathematical statement true. Let's simplify this expression into a x squared plus bx plus c form so that we can plug it into the quadratic equation. The first thing I'm going to do is to cross multiply the denominator. Then I'm going to FOIL out the term on the left and the term on the right. Then I will collect all the variables onto the right side of the equation. This is a quadratic equation. You can see it's an x squared function. It looks something like this, and now we need to find the roots. So where y is equal to 0. What is the value of x where y is equal to 0? This equation again is in a ax squared plus bx plus c form, and we can plug it into our quadratic formula given here and solve for the roots. When you solve the quadratic formula for this problem, you'll get two roots. The first root is where you subtract the terms in the numerator and you get 0.421283. The second root is when you add the terms in the numerator, and there you will get negative 2.26741. There are two solutions to the quadratic expression for this problem. Both of these solutions are mathematically correct, but only one of them has physical significance or makes sense for this chemical system. To figure out which one is correct, let's return to our initial change equilibrium table that we wrote before and plug in these root values for the equilibrium concentrations and see if we get reasonable values. If we start out with x equal to negative 2.26741 and plug that in and calculate the equilibrium concentration of HCl gas, what we find is that we get a negative molarity. We get a molarity of negative 3.9348 molar. You cannot have a negative concentration. The number of moles cannot be a negative number, and the volume cannot be a negative number. So that particular root doesn't give us an equilibrium composition that makes chemical sense, so we can reject it. Let's look at the equilibrium concentrations using the other root. Using the other root, we see that we get very reasonable equilibrium concentrations, all positive quantities. The next step would be to check our answer, so we should plug these equilibrium concentrations back into the law of mass action and make sure that we return a value of the equilibrium constant. Let's go back to our table of initial change in equilibrium and think about what would have happened if we had decided to have the change variable be positive x, or positive for the reactants and negative for the products. That would have changed the sign in our law of mass action, and so it would have looked like this. But if you do all the algebra with this new law of mass action with the flipped signs, you'll find that you'll get the same magnitude of the roots, but their signs will be flipped. What that means is when you plug it back into the table, or the equilibrium values in your table, it will flip the sign that was incorrectly chosen, and it will give you the correct answer. Again, the important thing is that the sign of the change variable is the same for all the reactants, and that the sign of the change variable is different for the products, and that it, again, is the same for all the products.